Okay, thank you so much. And I would like to start by thanking all the organizers for putting together this very stimulating program. And I have learned a lot from the previous talks. And hopefully that I can contribute positively to this workshop. So in this talk, I will describe a class of selection rules without group actions. And I will explain that how we might be able to understand them from the perspective of Spurion analysis. And so this talk will be based on a couple of papers that we did in the last year with my fantastic collaborators, Moto Suzuki from CISA and Hao Zhang from IPMU. And also in the process of doing this project, we also drew a lot of inspiration from a previous paper did by Hao and also his fantastic collaborators, Justin Kaidi and Yuji Tachikawa. So if you are interested in this topic, please check all of these papers. So perhaps this slide is totally unnecessary for this audience. That we know that we all love symmetries, and also, as pointed out yesterday by Nasanio's discussion sessions, we love symmetries because of many different reasons. For instance, like symmetries can impose conservation laws. And symmetries can be used to classify the physics of matter and phase transitions. And also symmetries can be used to understand the smallness of couplings and their stabilities of RG flows, under RG flows. And also symmetries may impose important constraints on the renormalization group flows. And so, and of course, this list goes on and on. So in case that we have more symmetries, then we have the more controls on the quantum field theory. And in particle physics, the very basic observable that we are interested in, of course, is the scattering amplitudes of dynamical particles. And suppose there's some bunch of particles coming in, and we are interested in the problem of what kind of bunch of particles will come out from the scattering process. And this kind of scattering amplitudes are typically dictated by the symmetries. And the symmetries we are used to, of course, described by groups. So by saying that, I have to, first of all, impose the group G and assume that each dynamical particles in my theory transform under some representation of this group. So the particles, the external dynamical particles are labeled by the representation of G. And usually that we say that such a scattering process is only allowed when there's a singlet representation being obtained from the tensor product. More precisely, it means that there should be an invariant tensor, which is used to contract all the indices of the external dynamical particles into a singlet representation. So this is the laws from the groups. And as we know that one can always construct a more complicated amplitude by gluing together some external legs of two simpler and more fundamental sub-amplitudes. And in string theory, in perturbation theory, that what we do is that we just glue together these two legs in conjugate representations. And the philosophy is that the full amplitude obtained by this kind of gluing will also preserve the group G in case each of these sub-amplitude preserve the G by themselves. And perhaps the very easy way of saying it is so-called from the Spurion analysis. The idea is very simple, that we simply promote a coupling constant into background fields, and in case the sub-amplitude is preserving the group G, then the coupling will be a singlet under this group. Then, of course, the tensor product of singlet representations will always remain as the singlet. That's why that usually the group-like selections will not be violated when we construct more complicated amplitudes from simpler ones. So different from the group-like selection rules, in this talk, I will describe a set of selection rules coming from the fact that particles are not in the representations of groups. And this perhaps is the most important sentence in this talk. So instead of assuming that we have a group G and require that the particles transform under some representation of the group G, we will instead consider a fusion algebra that we denoted by curly A. And the assumption is that I assume that each external dynamical particle phi will be labeled by a basis element within this fusion algebra. And so far, this statement may seem a little bit ambiguous and unclear. So what I decided to do is, in the next few minutes, is first to introduce the formalism, and then we are going to make some remarks by comparing with the ordinary group-like selection rules, and hopefully that in the next couple of minutes that these two sentences will be clear. So since that the basis element of this fusion algebra are typically non-invertible, so we decided to call this class of selection rules as the non-invertible selection rules. So what are those fusion algebras that I believe that some people in the audience know much better than I do? But as a particle physicist, that at least I gave a kind of a description from my perspective. So let us start by considering a finite set of basis element, which must contain the identity element and also some other elements which are not the identity. And these elements in this set should obey some fusion rules. What it describes is that suppose I bring together two elements. It had better be decomposable into a linear combination of all the other elements in this set. So basically, this selection rule is saying that x multiplied by y is a linear combination of z. And here the n is the so-called structure constant. And in case this is a linear combination, that the requirement is that this structure constant should be non-negative integers.
But by basis, you don't mean generating set or something. What do you mean by basis elements? Just elements?
Yeah, these are the x, y, z coordinates, right? Then one can do a linear combination of them on the right-hand side. Yeah.
Okay. But is it going to be important that these are integers because one can consider more general algebras for which?
Well, in case they are not integers, they are called hypergroups. And yeah, I'm not going to use that. So,
well, whatever you call them, but
yeah,
in physics, in the end, it's going to be important, I guess, what kind of objects occur in physics.
Yeah.
So we know that this sort of things occur, but what about things with reals? Can they occur somewhere as some interesting physics problem, not to you?
I don't know. I don't care in this talk. Yeah.
Surely not real, but complex physics.
No, I mean in this talk. Sorry. Yeah. In this talk, I will just make these assumptions. Okay. There are more general structures that it is possible, indeed. And so. Usually when we describe which particle interactions are allowed and which are not allowed, usually the order of this, the order of those external particles will not be important. So, because of that, I will assume that these fusion rules are commutative. Okay. So the order of the fusion is not important in this talk.
Sorry, this capital A is the same as the curly A in the previous slide?
No, the curly A is the algebra. The A here is the set.
Okay.
Yeah. And okay, so typically for basis element X, there will exist no inverse of that element such that their fusion product equals 1. So typically those basis elements will be so-called non-invertible elements. And moreover, even despite that they do not, there isn't any inverse, but I will assume that for each element, there's a conjugate element, which I denoted by x bar. The requirement is that I obtain the identity element in the fusion of such a conjugate pairs. Okay, so the fusion of x and x bar is not 1, but the 1 is contained as one of the element on the right-hand side of this equation.
1 times 1 or anything times 1? on the right-hand side.
Right.
What's
You
the
insist that the
multiplicity?
structure constant be 1 for the unit.
The structure constant doesn't have to be 1. It can contain multiple copies of the identity. That's also possible. So let me immediately give a very simple example. Maybe the simplest fusion algebra that I can consider is an algebra with 2 basis elements. They are identity and tau, and they satisfy the selection rule like this. Okay. So from this algebra, that one can see that the identity is an invertible element, but tau is not an invertible element. So tau is non-invertible, and both of the basis elements will be self-conjugate from this algebra. So so far, this is just a mathematical object that we described. How we use them? Then how do we use them in describing the interactions of particles? As I emphasized that since all the external legs should be dynamical particles, maybe the very minimum requirement is that the kinetic term should exist, right? So because of that, the first thing that I might require is that the particles and antiparticle pairs should be labeled by the conjugate element pairs. And more generally, in case that the particle interactions are considered, then the vertices, I require that the vertices is only allowed in case that the fusion product of that vertices should contain the identity element, and where in these vertices each particle is labeled by such an element. And all these kind of vertices, I can view them as minimal building blocks for constructing more complicated amplitudes. Okay, so this is the selection rule that I will impose.
Do you impose this at the level of particles or at the level of fields?
I think that at level of particles.
Yeah, my question is sort of similar to Slava's. Like, do you assign an operator, which is say phi to the n, to have some definite representation, some definite fusion?
I think it's just the particles in the scattering process that I'm assigning. Maybe you're worrying about that. Maybe if I use a Lagrangian description, there may be filter definitions and something like that, right? But here I'm assuming that the particles,
Then basically your whole setup is just perturbative if you only think in terms of particles.
Yeah, I mean perturbation theory, yes. This is the problem that we are interested in particle physics, basically.
That work.
Do you don't know or do you not care again?
Sorry. Yeah, I'll be interested in this talk only perturbation theory.
Sorry, but why is it perturbative?
Because particles is a kind of excitation of a fixed point.
I think it doesn't need to be perturbative, right?
But also the punchline of this structure will be that it only holds up to some level in perturbation theory.
If you assume that all amplitudes can be constructed from lower other amplitudes by gluing, then this is a perturbative setup.
Yes.
Yeah.
I agree. So far, just this structure doesn't need to be this requirement that if the amplitude is invariant, if the identity is in the product. I think that's a more generic statement.
Right, but I think that the setup, it's ambiguous what fusion algebra element you would say phi to the n transforms it.
Yeah.
Maybe you don't care.
No, let me say that in this talk I'm interested in perturbation theory, and particles are indeed excitations of free fixed points. Okay, so let me say that for the moment I.
So it's not Lagrangian selection rules you're talking about.
Eventually, that I'm going to use a Lagrangian at the end, but.
Isn't that you have to say what Clay was asking about?
Yeah.
To the end. What about that?
Yes, so in doing Spurion analysis, eventually, it's very tempting to use a Lagrangian. But the selection rule itself, I think I will interpret it as the selection rules on the particles in the scattering process. That maybe is the most physical way of saying it.
Okay. Are your particles created by an operator?
Yes, and
so then you can talk about how this operator transforms, right?
Right, and you may also do filter definitions, right? About the, there may be different interpolating operators which can create the same particle.
Okay. Yeah, so like equations of motion sort of things, for example.
Yeah. These are all possible. So it seems to me, yeah, indeed, it becomes ambiguous if I impose these selection rules on the fields in the Lagrangian. But I think this is a more physical way of saying that.
No, it means you didn't learn field theory. Saying that we cannot talk about symmetries at the level of fields.
No, we can. No, I say it's more ambiguous.
It's not ambiguous.
Or it's subject to, it's not ambiguous, but there will be issues from the field redefinitions and equation motions and something like that.
Yes,
It's also not claiming these are symmetries. They're selection rules.
Yeah.
And they're not going to be symmetries, is what's going to happen because of this relaxing of the group structure.
Okay, we just wanted to test the setup for it.
Okay.
Well, what's the issue? What's the subtlety that you actually just say these are fields that I associate with element? What is the problem with that?
The problem is that in a Lagrangian description, you can do field redefinitions.
But you can always do field definition, and then your symmetry is not manifest anymore if you mess things up. This is not. Yeah. But it's up to you as a physicist to choose a field basis in which the symmetry is manifest and work on that basis, and that's always possible in the cases that we're familiar with.
Yes.
And if you just did some field definition which messed things up, well, that's your fault.
Sorry,
Maybe are these selection rules exact or approximate selection rules? Because if they're approximate, then there might be issues.
Right. So this usually only works to some order, I think.
Yeah. You already anticipated, so yes.
Maybe let's proceed for now and you can assess it.
Yeah, indeed, it's a very important question. Yes. Yes, and so maybe at this point, to just I don't know whether it's clear, it's useful to clear up any kind of confusions, but let's just make a couple of comparisons between the ordinary group-like selection rules and also the selection rules that we are introducing in this talk. So if I usually when we say that the selection rules are described by groups, actually it has two parts. So the first that the representations of the group has to satisfy the tensor product, and secondly that the particles, since they transform under the representations, they should carry the indices of that representations. And here in this set of non-invertible selection rules, it's kind of that we only keep the first layer of the structure, which is the structure very similar to the tensor product of the representations. As you see that these two equations are very similar, and but however that we completely discarded the structures of the representation indices. So there isn't any Clapeyron Gordon coefficients or any invariant tensors that are used to construct the indices. Okay, so that's maybe the main difference. So based on this comparison, that we can say that this set of selection rules maybe is more minimal, but precisely because it's really minimal, that it's going to be less rigid compared to the ordinary group-like selection rules. To appreciate, perhaps let's consider such an example. So let's just consider just a bunch of SU2 representations.
Sorry, before you go, can I just add this question? When you discard the structure of representation indices, you impose that as a rules of the game. Or is it the outcome of something? Or
well, it is a rule of the game in the very beginning, and that said the particles are not in the representation. Right.
Okay, but then when you say
they do not transform under the representation.
But you promised that you said you would explain why that would be natural, but I haven't seen why it's natural to say that.
Well, the natural is saying that this kind of the fusion structure. Actually, we are all familiar with that. That is nothing but just the same structure of the tensor products of the representations. So under the tensor products, the representation themselves can be viewed as the fusion algebra.
But if, for example, if my fusion algebra was secretly a discrete group, a finite group, then I wouldn't suddenly say that my particles would transform, like you would attach elements of the group to the particles, right? You would say, well, we have to build now the representations of the group, and the particles are going to transform as into irreducible representations.
Right.
So I would think that if your theory has some Fock space structure and some fusion category structure, then you would have to first build the irreducible representations of this fusion category in some way, and then say attach some label like from this set of irreducible representations, or it's equivalent to the particles, not elements.
Yeah, indeed. So if you have a kind of a symmetry behind, and you have the idea of how the symmetry acts, then it's very natural to build something which is invariant. Then from that requirement that the particle should be in the representations, right? But however, I'm here doing something which is more minimal. The word natural, what I mean by natural is saying that these structures actually we are all familiar with.
Well, it's more like you're taking the category, the fusion category, that's the rep of the original fusion category that you started with.
Right. And also, let me also say that this is...
It can never be commutative, right? Because you can take anti-symmetric products and symmetric.
Yeah, but I'm assuming that they are commutative in this talk.
Yeah, so that seems like a big assumption too.
So probably I lost it. Can you explain again the difference between phi I sim Ri versus phi I sim Xi? What are the difference of these two?
The difference is that here the phi I should carry some indices of these representations because they should transform, right? Okay. They are in the representation. But here below, the phi I doesn't carry any indices of the representation since they are not in the representation at all.
Does the particle carry any quantum number under that fusion category?
Well, the particles only are labeled by the element.
Maybe this example is instructive. I think if you explain the example.
Okay, so I will play.
Yeah. So let's consider a bunch of SU2 representations. These are perhaps the simplest representations. And so as far as the first layer of this structure is considered, then you might think that you are able to construct such a diagram where the mixing between the singlet and the triplet is going to be induced by a loop of the triplet. But however, that in case the full SU2 symmetry is considered, in the sense that if the particles are really transforming the representations, then they carry the indices of the SU2. Then in order for such a diagram to be allowed, there should be invariant tensor which are used to construct the indices of the singlet representation and the triplet representation. However, there isn't any invariant tensor of the SU2 which can do the job. So in this way, that in fact such a diagram will be only allowed in the second case, but not be allowed in the first case.
Okay. Can you just understand? So it seems to me that you're doing two things. First of all, you take your triplet, and then you kind of forget that it was a triplet just assigned to every particle in this triplet. You just assign this new label 3.
Yes.
And so there are actually 3 particles in the triplet. So
well, actually, it doesn't have to be 3 particles. It can be only one particle.
In this particular example, there's going to be 3.
Yeah.
So you started with a theory which had SU2 symmetry. There was a single triplet, so there were 3 particles.
Yeah, if I assume that SU2 symmetry is the transform on the triplets, then there should be 3 particles. But here, if this layer of the consideration, then I can say there's one particle labeled by 1, there's another particle labeled by 3, right? And I can impose an algebra which has the same structure as this kind of tensor product. Then this diagram is allowed, right? But the particle here doesn't have to be doesn't have to be triplet. It can only have just one component.
So I guess the question of Balt was, suppose that such a structure exists.
Yeah.
And you insist on doing it your way, not constructing representations of the fusion algebra. Is it just because you are being lazy? No,
this is more minimal. No, this is more minimal. We can.
Does it really exist? Because if it's more minimal, but it's only more minimal because you are being lazy.
I think maybe you're just saying you could try to construct an invariant tensor and fail, but if you just look at the fusion rules, you can tell that ahead of time. you don't have to do all the hard work of trying to construct an invariant tensor.
But then it's going to fail at some loops. Why is it failing? Because you didn't do your job properly.
In the case of a group-like symmetry, yes. But more generally, I think.
More generally, more things can happen. Yes.
That it doesn't come from a group and it will just break. Period. At some loop order.
Yeah. It broke maybe because, in fact, there was some extra selection rules that you did not impose. Because of this representations.
They want to claim there are situations where you don't have actually the group-like symmetry, and you only have this more minimal selection.
No, but group, even for fusion categories, have representations.
That's not this. It's what.
It's not this
rep of whatever that thing is.
This is a completely different thing. If this analogy is to be believed, that bottom line 3 times 3 is 1 plus 3 plus 5 is a statement in the representation ring. And if you're trying to make an analogy with that, this talk has got nothing to do with fusion algebras and representations thereof.
Yeah, indeed. So I think what Slava said is correct. But I would not say I'm more lazy, but I'm more open-minded to consider.
I think that the name is just a bit confusing because you would think that non-invertible selection rules come from non-invertible symmetries, but this is not necessarily the case, right? This is not a selection rule coming from a non-invertible symmetry.
Well, in fact, some string theory would say yes. Actually, this is a conversation that I had with my friend Hao, that he drew my attention to his paper, and they say, well, this even though they are kind of minimal and from the selection rule themselves, you don't see the non-invertible symmetries at first glance, but from their perspective, that they say, well, they will originate from some non-invertible symmetries of some string wordsheet theory.
In case the non-invertible symmetries in space-time. It's like
right.
Symmetries of the wordsheet are gauge symmetries in space-time.
Right. So, yeah. So this is their perspective. But as a particle physicist, I will just work from the bottom up. As already anticipated by a lot of people in the audience, that maybe an important question to understand is that how rigid are those non-invertible selection rules? As we already mentioned, that one can construct more complicated amplitudes from the simpler building blocks. So let's start by such two more simpler building blocks. Each of them satisfy this fusion algebra. So the first one is that all the product of the external legs should contain identity, and since then one can consider the product from x2 to xn, and since one can expand this product in the basis element, since eventually that you want to get identity by multiplying one more element, which is x1, so in this fusion product from x2, there should be at least containing the conjugate of x1. And similarly, you can work out for the second amplitude. So by combining these two equations, then you will immediately see that the unglued external legs should also contain the identity in their fusion product. So the conclusion is that if I construct the three amplitudes, that this kind of selection rules will be preserved. Okay? Since I didn't specify any specific structure, and this conclusion is completely general at tree level. So what about at loop level? As we already seen in one example, but here we can phrase it more generally. So let's consider there are two elements which are not conjugate to each other. So because of that, then the identity element is not contained in their fusion product. So I will say that in case there's a particle labeled by X and particle labeled by Y, their mixing will be forbidden at tree level. However, that such a mixing of the two particles may be induced at loop level through the diagram like that. And here the important point is that the particles propagating in the loop must be labeled by the non-invertible elements. So how do we see this statement? One can do that, for instance, by cutting the loops into such a tree diagram. And since the order of the fusion is not important, I can just deform it into this diagram. And eventually that we glue back the conjugate pairs that we end up with the last diagram. So the point is that here the element Z, which is produced by the fusion of the conjugate pair, should not be the identity element, such that by dressing this element, I can identify two elements which were originally different. So in case this element U is the invertible element, then this Z must be the identity, and hence it cannot be used to identify different elements.
So I think I missed some. What do you mean by deform?
Well, this is like a F move, which connects to different fusion channels.
Is it an assumption that this can be done?
Since here the order of the fusion is not important, so I can always do that.
Just from associativity, you can prove that this is possible?
Yeah, I think so. Why not?
It's viewed as, I mean, it is a view, U, bar, you just change the order of the multiplication and then just a arithmetic representation of that change of order.
Yeah.
So, but should I view this as a Feynman diagram or your diagram? In the sense that this is
this is amplitude in a sense. Well, this is capturing the selection rule information of an amplitude.
So I shouldn't really view this as a Feynman diagram.
Right.
You should, okay.
Yeah. I don't know what diagram should I call anyway. So here, if you are more careful, that you will notice that actually we imposed two hidden assumptions. The first one is that I assume that the selection rules are faithfully realized in the sense that each element in the fusion algebra should label at least one particle. The idea is that suppose that the particles propagating in the loop completely decouple, then it cannot induce the mixing like that, right? And secondly, that I assume that the particles here do not carry additional quantum numbers. And in case that there are additional quantum numbers of selection rules are imposed, such a process of identifying different elements may also be obstructed. For instance, like if the particle X is a kind of a boson and Y is a fermion. And of course, that we know that in case of Lorentz invariance, and this cannot happen. So how do we understand this constraint of the selection rules in a general loop order? So one can consider such a diagram, such an amplitude at loop level n, and we play the same trick by just making n cuts to make it into a tree diagram, and this tree diagram will contain the original external legs plus n additional conjugate pairs. And these conjugate pairs just come from the cutting of the internal lines of this original amplitude. And by doing the same trick, I can deform now the order of the fusion and pull out these conjugate pairs, and I have this diagram. And eventually that I just glue back the conjugate pairs. So the constraint of the scattering process at loop order n is allowed that suppose that the original external legs contain some element, such an element should also be obtained in a different way by the fusion of those conjugate pairs, right? As the order of n is increased, that the set of this element V will be larger and larger. So you will see that this kind of constraint will be weaker and weaker as the loop order is increased. So indeed, that many people were correct that these selection rules will not be preserved at the loop order.
But do you really mean a V in the W chain or V bar? You have to cancel V.
Well, it depends on the arrow of this line. Yeah, whether it's a
product of that has
yeah.
So what do you mean that it's not going to be preserved?
Well, if this is a tree diagram, the requirement of satisfying the selection rule is that the product of the external legs should contain 1, right? Contain identity. But here, since this is an n-loop diagram, as we see from this kind of diagram, so we see the requirement is that the product of the external legs contains some other element which is not identity. And these elements are in general produced by the fusions of those conjugate pairs, right? this set will be larger and larger as n is increased.
Okay, so for every loop order, you get your own.
Yes.
But it's still a valid rule.
Yes, you can construct in this way. Yes.
But it's less and less constraining.
Because the set of this element will be bigger and bigger.
Yeah. But can it happen that actually it is as constraining as the original one? For some specific.
Yeah, then you need to obstruct this process by imposing, for instance, like by requiring the particles are transformed in a complete representation. Then we know that we going back to the ordinary case of the group-like selection rules. Then it's never violated. So the game is that you start from the most basic structure, and you can try to understand how to obstruct this process.
Is the claim that if the selection rule is genuinely non-invertible as you're defining it, it's strictly weaker?
Yes, weaker.
Strictly.
Yeah. I think this is the weakest thing that you might have, because I only imposed the one layer of structure, right? And yeah.
And there's something I'm confused about, because I thought that if we really had a non-invertible symmetry, then there had to be some sort of selection rule.
Yeah, but I'm not having a non-invertible symmetry.
Yeah, but you're only contrasting usual group symmetry with this selection rule.
Yes.
Isn't there in the middle somewhere a non-invertible symmetry, which should be a little bit in the middle, or no? No?
Well,
there's
I
no.
don't think so. Yeah.
There's nothing in the middle.
In fact, the original paper, Justin and friends, they just said, okay, you look at the Lagrangian, that tells you what these fusion rules are, just based on which vertices you have in the Lagrangian. Like if I put two of these together, what can come out, and that's what I call my. There's no symmetry.
So basically, the claim is that whenever you have a selection rule which is the same at all loop orders, you must have group symmetry.
No, you can.
You must have a symmetry, I would say.
Sorry?
Even if it's group-like, you must have a symmetry.
The non-invertible chiral symmetry is acting invertibly on the zero form, on the loop operators.
Well, it depends on the dimension.
Sure, sorry, 40.
Also, in 40, in principle, there is zero form symmetry acting non-invertibly on local operators. But anyway.
No, but not anyway, because I'm confused. Sorry. Because so we jumped from something which we are very familiar with, and it works perfectly at all loop orders, to something which is not a symmetry and only works worse and worse at high loop orders. Now you guys tell me that actually there is some symmetry, non-invertible, whatever, which is going to work at all loop orders. And because it's non-invertible, it's going to be formulated in the language of fusion categories in some way.
It won't be this fusion category.
Well, what kind of, how different? It's going to be very similar, no?
Well, it's the same relationship is what Val was saying. There's G and there's rep G.
Yeah.
Right? So G is like an invertible fusion category, it's group-like. Rep G in general is not.
Yeah, and so, but can you formulate things?
Yeah, I would say that in that case, you would have whatever rep of the non-invertible symmetry is, and then you have to build invariant tensors under that.
Yeah.
And
I think this is a way to understand things constructed. You can start from this minimal structure and then pose more structures, and you get something more rigid, very different questions.
Okay, thank you.
All right, so let's connect to Spurion analysis. So, these diagrams are all very nice, but from a particle physicist, it's very tempting to do it from a different perspective, basically from Spurion analysis, as Nathaniel yesterday already discussed. So the idea is just to promote the coupling constant in the theory into background fields. And by doing that, the final goal would be to keep track of all these couplings in all the tree and the loop processes. That's the ultimate goal. And now we're just applying this idea to this class of non-invertible selection rule. And as we will see, that in order to really understand the radiative breaking of these selection rules, that I have to promote the coupling constant into some suitable non-trivial labels of this fusion algebra, as I will be more precise. So our goal is to understand how come that the tree level exact selection rules will be broken at loop level, and also to track all the couplings in the arbitrary scattering process at any loop order. And in our papers, actually, we have surveyed through a couple of different fusion algebras, and they include the near group fusion algebras. Basically, they are the algebra which contains the elements of the group, and also with another non-invertible element, which I denoted by rho, and they satisfy the selection rule like that. And they include the familiar Fibonacci-izing, RAP-S3, Tamburaya-Yamagami of abelian group G, and so on. And we also surveyed the conjugacy class of the S3, and eventually the Z2 gauging of the ZM symmetry. And noticeably that this class of selection rules were used quite a lot in recent literatures in understanding the texture zero structures in the Yukawas and also the radiative neutrino mass models.
Sorry, can I ask?
Yeah.
Not all near group fusion algebras have your assumption that x times y is y times x. So what happens if you relax that?
Well, typically, when we say that interaction is allowed or not, the order of those external legs should not be important. That's the usual case.
So if there is one...
if you want to describe some interactions, if you want to describe some interactions which depends on the order, then you use a different algebraic structure.
At the level that you're working, could everything have just been a ring?
Yeah, this is the key confusion, is that this is just to talk about rings, and you take the representation ring of a group, and you forget everything apart from the fact that the product of two irreducible representations decomposes into a sum of positive integer combinations of others. And you just keep that bit of information and generalize it to things which are not rings.
For instance, could we have relaxed the integrality and it would have all worked still?
Sorry, relax what?
Was there any reason in what you're applying so far for n, x, y, z to be an integer?
I think this is just more natural, but there isn't any specific reason why it should be. Well, because n naturally just account for the multiplicity, right, of the element you obtain from that fusion.
Well, in a more rigid setting where we're trying to impose various other axioms, that's of course natural. But I'm just trying to understand how flexible this framework is. Could it, for the purposes of assigning selection rules that hold iteratively at some order in perturbation theory, could we have worked with just a fusion ring?
How do you say if the product contains a singlet if it's like a half times it?
Yeah, that's described by hypergroups, in case you know. But it's a little bit, well, I find it a little bit unnatural to say that half of a singlet element obtained from some fusion.
But the meaning of the coefficient is, there's no meaning to the coefficient in your analysis, is there? Like
No.
You're saying as long as it's non-zero, then you define this inclusion symbol.
Yeah. If you had a coefficient 100 in the fusion product, you're not using that 100 anywhere, are you?
Right. Exactly.
Okay. So it does sound like it could have worked for more general coefficients.
Yeah, square root 2, for instance. But I find it unnatural to say a square root 2 number of identity elements.
He's saying it's a generalization of your generalization, which also works perfectly well.
Right.
Yeah, but the question is, are there any, I think what we are saying, there are some interesting algebraic objects out there which will allow you to define more general selection rules. Okay. Now, you tell them that it's unnatural, but in the end, the question is, are there any interesting questions in particle physics? Since you're a particle physicist, then you could say that. Are there interesting questions that you could address using such more general rules?
I think this is a fantastic question.
Yes.
But I don't have an answer. Indeed, we should be more open-minded. That's the secret of this talk. Yeah.
But more important to the particle physics, is there something that you can explain with this that cannot be explained?
Yeah, I was gonna exactly ask this question.
Oh, okay.
You see, so if you go to the previous slide, you listed this texture work.
Yes.
If you play the game with a group, it's so hard, right?
Yeah.
In fact, there is not even successful single acceptable, like universally happy model.
You see, there's so many papers, you're so relaxed that you basically can find some fusion category, can fit into whatever texture you want to explain. Right. So instead of you have a, I impose this selection rule and there's a predictive power, constraint dynamics, you can basically, seems like explaining any pattern you like in a sense, because you can relax all these things.
But for these texture zeros, I haven't studied it very carefully, but my impression is that this is not very different from I'm just going to decree, I'm going to set it to 0 at tree level. And it's going to be violated at the one loop anyways.
Yeah.
So it's not really different from that same.
No, but he can control the loop order at which it is violated. So that's something new, right? He can tell you. Yeah. He can tell you that he can tell you an algebraic condition for it to hold to 3 loops if he wants.
But in practice in this literature, they haven't done that.
Well, but it's something that would be built into this algebraic framework.
But also there is another way of understanding this. Usually it's like some collective breaking story. Yeah. Right. You can just basically construct the state from my theory. I can only draw diagrams like this. I guess maybe this is a more systematic way of
yeah. This is a more constructive way, I would say. Yeah. How yeah. You can do collective breaking of that too, in case you want. You can place different elements in case you have multi-site models. Then you just put elements on different sites, and the locality of this extra dimension can play some role.
But that can also be done by collective breaking. The question is whether there's any surprise if you do this, right?
Then we have to survey all the parts. Yeah, I didn't know. Yes, indeed. How am I doing with time?
You started a bit late, 15 minutes roughly more.
Okay. Yeah, maybe I have to slightly rush a little bit. Well, because of the interest in the recent literature, and this is the algebra that basically I will focus on in the rest of this talk. And some people may be familiar with it, that this structure had this structure is very similar to what's so-called cosine symmetries in the literature. So the idea is that I have a set of elements, and the fusion of these elements satisfy such a condition. Basically, you just add and subtract the indices of each of these elements. And one interesting observation is that you can just think of these elements as a kind of cosine functions. And such a fusion actually takes the exact same form of the ordinary multiplication of those cosine functions, right? From those trigonometric identities that we all know. So except for some special cases where the J is either 0 or m/2, and all the other elements are non-invertible. And also all the elements here are self-conjugate, since that the identity is always produced by the fusion of each of the elements by themselves. So now I'm going to switch to the Lagrangian description eventually. So it's hard to not to do it. So under the assumption of one, that the fusion algebra is faithfully realized, and secondly, that there's no additional quantum numbers considered, then it's very natural to write down a Lagrangian like this, with the requirement that each of the particles is labeled by element in the algebra, and it contains the identity in the fusion product. And here I write down a very specific example for m equals 5, and I write down all the interaction terms at the renormalizable level, which is consistent with this fusion algebra. It looks like it's a whole piece of mass here, that all of these terms are consistent. And each of these vertices can be viewed as a minimal building blocks for constructing the more complicated amplitudes. So the question is that in the Spurion analysis, in case we view each of these coupling constants as a background fields, how do we promote them and label them using the elements in a consistent way? For instance, then one can ask, since all of those terms are consistent with the algebra, can I label all these couplings using the identity element? Right? This is the most naive way of doing that. And however, since the selection rules will be eventually violated by the loops. So in fact, that we cannot really label all the couplings using identity element, even though the fusion algebra is exacted from the very beginning. So in order to really label the couplings consistently, let's very quickly make two observations. The first observation is that I should first remove all the conjugate paired labels in the vertices. And in other words, that all the conjugate pairs of labels for external dynamical particles should be labeled by identity. The reason of doing that actually is very intuitive. For instance, like we can consider the following two vertices, and the only difference is only the conjugate pairs. And by any way, the first by closing the loop of this conjugate pair, one can always obtain the second vertices from the first vertices, as seen, for instance, like the graph like that. So it means that here the two couplings should be really labeled by the same element, right? So it means that the rule is that in case there are some conjugate pairs appearing in the vertices, then they should not be considered when I try to decide how to label the coupling constant. And the second observation, maybe it's a little bit harder to see in the real time. And since we make the assumption that all the elements are self-conjugated, actually I can introduce a Z2 valued function which captures the information whether each individual element is a paired or not in the vertices. So I just assign this function to 0 when the element is paired, and assign this element to 1 if the element is not paired. This is just a fancy way of saying that there is a Z2 group that captures the information where in each vertices the element is paired or not. Of course, in the general vertices, as we've seen in the example, this Z2 is going to be very badly broken. And the nice feature of such a function is that suppose I try to construct an amplitude by gluing two sub-amplitudes at tree level, and this function x satisfies a very nice property of this equation. And this basically is captured by some sort of Z2 structure.
How is the element C used on the right-hand side?
C, because C doesn't really matter in this story. It means that this identity is valid for whatever legs I glued. So by combining the two observations, we propose the following in the paper for labeling all the coupling constant consistently. So the first is that we remove all the paired labels. And then the second step is that we label the coupling constant using the fusion product of the remaining unpaired labels. So this is the outcome when applied to the previous example that I have written for the special case when m is 5. So within all these pieces of the vertices that allowed, all the couplings here are labeled by the identity element except the following, which I highlighted in particular in red. And by applying this rule that all these couplings highlighted should be labeled by the elements like here. Okay, so the advantage of that is that it automatically follows the following fact is that suppose I construct two amplitudes, and I glue the two amplitudes together to construct a more complicated amplitude. In case I view this full amplitude as vertex, then the labeling of the full amplitude, the coupling of that full amplitude should be contained in the labeling of the coupling of each of the sub-amplitudes. So as in this example, for instance, we can see that there's such a 6-leg amplitude which is obtained from the product of these two 4-point amplitudes. and one can explicitly check that their labeling satisfies such a relation. And this basically completes all the discussions at the tree level. Now let's just try to move to the loop level. How do we understand the loop level is the following. So let's start with a loop amplitude. I can make n cuts to make it a tree level amplitudes. Since first that we have saying that the presence of the conjugate pairs should not be important for us. So the labeling of the corresponding couplings should not matter whether there's whether there will be additional n pairs of the conjugate pairs. So this means that the label of the vertices should be remain the same before and after the cuts. And by combining the previous result, which is valid at the tree level, I ended up with such a relation. So one can immediately check this relation. For instance, I can consider the mixing between the G0 and the G1, which is generated at two-loop level from the two 4-point vertices. And one can see such a relation is valid. Okay, before we conclude, let's just make some applications very briefly. So the first, of course, is kind of inspired by the recent literature that some people studied some texture zeros of the Yukawas. And actually, they write down some texture zeros, but none of them are actually exact up to all loop orders. And in particular, these 3 zeros will be generated one loop, and this 0 will be generated two loop. And one can check with the labels and of the couplings, and also the validity of our labeling scheme in the Spurion analysis at both end 1 and 2 loop level.
So,
yeah.
Sorry, the papers you're selling were already using this kind of
yes.
fusion algebra.
Yes. Yes. And so before I finally conclude, let me try to make an observation that this set of selection rules may also impose some constraint on the renormalization group flow in perturbation theory. For instance, that again, we use the same fusion algebra. I can construct two theories. One, I call it as the phase 4 scenario, which contains the 3 particles, phi 1, phi 0, phi 1, and phi 2. And I write down all the possible interactions which are consistent with the algebra. And secondly, I constructed that I call the unphase 4 scenario, which only contains the 2 particles phi 0 and phi 1. And I write down all the possible terms that are allowed. And the question is that can I really flow from the first theory to the second theory by decoupling the particle phi 2? So this is the problem. The answer looks like yes, right? It's very natural that the algebra is the same and the spectrum and the particle are almost the same, except that the particle I try to decouple. And in fact, the answer is no. In case that the 2 Lagrangians are written as above. And there may be different reasons.
Can you explain what you mean by flow by decoupling? Giving mass to phi 2 and then just flow? As you said, RG flow and perturbation.
You send this coupling to infinity. I completely decouple the particle phi 2. Then the question is that if this theory flows to this theory. I mean, are these more quantitatively means that are these terms were reduced to these terms in the low energy limit if I send this coupling to infinity?
At the fixed loop part?
Can't we just, do one of the two things? For example, set this mass to some fixed value and then just go to the energies sufficiently small compared to that mass?
Yeah, it's the same. Yeah.
Okay.
Yeah. Yeah, that's a good question, as I would explain. Yeah. As I said, this is perturbation theory. There shouldn't be any surprises. I mean, I don't have to understand anything. I just compute. So the job is done.
But the point of selection rules is that you don't have to compute.
Right.
So
yes,
this is in between. There's diagrammatics, there's selection rules from symmetries.
Yeah.
This is something in between.
Yeah.
No, we know what can happen. We should just cross out this particle phi 2 from all diagrams. Is there something wrong with this logic?
Well, I don't think there's anything wrong because this is perturbation theory. You can do things in many different ways.
And so what happens when you cross out phi 2? Do you get this Lagrange?
Yes, yes.
But then why do you say this is not possible?
Well, as I will explain in the following. I mean, as the two Lagranges are returned as above, yes. So yeah, the way, my way of understanding is the following. So in the phase 4 scenario, that at the algebra level, that one can see that the particle labeled by G0 and the particle labeled by G1 are going to be identified at one loop level by addressing a conjugate pair, which is induced by a particle labeled by G2 propagating in the loop. That's the diagram that we saw before. And that's what happens in the UV theory. And what happens in the IR theory, because there isn't any particle which are labeled by G2, the only way of identifying the G0 and G1 is through such a relation. I can only do it by addressing 4 powers of the particle labeled by G1. And such a thing can only happen beyond one loop. So by inferring from the structure of the violation of the selection rules, I see that there's kind of a mismatch between the loop order, between the UV theory and the IR theory. So the mismatch between the two theories implies that in the IR theory, I must add something at one loop as like for the mixing of phi 0 and phi 1 in order to match the loop order of the violation. Okay, so indeed, such a vertex will be generated if you compute it explicitly in matching. But here we are only inferring from the algebraic relations like here.
Can you show how it's generated? Like, can you show us the Lagrangians in the previous page?
Right. Yes, so
so we are only assuming that lambda 2 is order 1 and all other lambda 0, lambda kinetic terms are order 1 and then all the interaction terms are small and then we flow. How can you generate order 1 mixing, kinetic mixing between phi 0 and phi 1?
There's a particle phi 2, right? Well, I think this is allowed.
But this involves cubic couplings, which I assume small.
I mean, all the couplings should be order 1.
No, I mean, that doesn't correspond to RG flow.
You mean you want to?
Here, I want to keep lambda 2 order 1, other couplings are perturbative. Lambda 2 is a kinetic term, so this is order 1. Other couplings are interactions, so they're perturbative. They should be much smaller than 1 over 4 pi.
Yeah, okay. Yeah. But the idea is that I'm saying that such a process can be generated at one loop, right? And this is understood at the algebra level, that phi 0 and phi 1. Here you address it with phi 1, and here there's a phi 2.
Okay.
Yeah. Yeah.
Okay, thanks.
Yeah, and secondly, you can do it, but you realize that it cannot happen at the same loop order. And by matching the loop order, then there should be additional terms.
But this is not a surprise.
Sure, this is perturbation theory. Nothing should be a surprise.
If you just deleting field is just tree-level matching. There will be something beyond that.
Right.
So
that's why I say this is one loop. This is one loop.
Yeah, but okay. This is not a surprise.
Nothing surprising. Yeah.
It's never a surprise, but it lets you predict when it will happen without drawing any diagram.
Yeah. You realize it immediately without doing any matching.
It is a surprise if some of those things is not in there.
But it could have been a surprise that it only enters a two-loop order.
Yeah. That would be a surprise.
Right?
Yeah.
Then you have to draw a diagram, but I think there will be some example like that. I don't know if it will show them. But
yeah. This one per se itself is not quite.
Yeah. So then we're just bored in the paper and made a conjecture. I'm happy to be I'm happy to falsify it in case anybody in the audience can do. So our general conjecture is the following. Suppose I constructed two Lagrangians using different fusion algebras, one in the UV and one in the IR. And the claim is that these two theories cannot be connected by the RG flow if the process of the violation, loop-induced violation of non-invertible selection rules are not exactly the same. So this is our conjecture.
So in order to make that claim, suppose I write a UV Lagrange.
Yeah.
you have to tell me there's a one unique fusion algebra consistent with the Lagrange. So if there are multiple fusion algebras are consistent with that Lagrange, how would I even say? That means I cannot even determine algebra.
Well, if one theory can be described by two different algebras, I think the violation will be the same. I'm not sure whether it is possible, first of all. In case it is possible.
At least this has to pass, right? Otherwise, you're telling me I cannot, given a UV, I cannot even determine uniquely algebra down to. That's your thing. No?
No, I'm saying one theory you construct using algebra 1 and other theory using the algebra 2.
Yeah, the same Lagrange, let's say.
No, different Lagrange.
Suppose with the same Lagrange, I suppose I can come up with the two different fusion algebra consistent with whatever term I have written down.
Yeah, how come this is?
The trivial RG flow, which is theory 1 goes to theory 1.
Yeah.
By doing nothing.
Yeah.
That's what you're saying.
But sorry,
this is the consistency.
Exactly.
The example you have earlier, is that an example you say it would be yes?
Yeah.
No, I thought that you exactly say that that two Lagrangian one flow to the other.
One flow to the other in the presence of additional terms. In case you don't.
RG flow, obviously, that's what you expect. Right?
I think what we can do is let's go back to your theory, the scalar field theory. Game number 1, I'm gonna do according to like QFT without a fusion algebra.
Yes.
So I can determine my IR Lagrange. That's a trivial fusion algebra game.
Yeah.
Game number 2, let's do the way you do. So it goes to different theory. Yes. Which means I don't even know if they're uniquely specified UV theory. I don't know which theory I'm flowing to.
In case
which theory would my UV theory flow to? IR number 1 without a fusion algebra, IR number 2 with your which one this year flow to?
Well, I think the algebra is useful when you make a restriction to exclude some possibilities.
The general reason is that if I specify UV, this theory should flow to unique IR theory.
Right.
Okay, but here I'm telling you that there are at least two.
Of course, that depending on the parameters that you can flow to different.
Well, UV is fixed.
Yeah,
I'm asking what is my IR theory?
Yeah, then depends on the parameter.
Is this about like the inverse problem?
Inverse is the hard, but I'm really doing fully to the IR.
Yeah, but I mean, their setup is start with a given fusion algebra, then write down the Lagrangian. You're asking, given the Lagrangian, how do I know if there's only one fusion algebra?
Yeah, that's how I phrased my question first, right? Yeah. But then I'm just literally saying this example. How do I determine my IR theory given this?
What's the rules of the game, right? That's the question.
I think you start from a Lagrangian and you want to determine where it flows. I think it depends on the parameters.
I specify parameter everything.
Yeah, at the algebra level, you have an algebra in the UV, right? And there may be different sub-algebra of that algebra.
I don't know if there's algebra or not.
But this isn't a sub-algebra, right? Because phi 1 and phi 0 fuse into phi 2.
Maybe we can let him finish and then we can...
Yes.
Okay. Yeah. Anyway, and the flip side of this statement is that one can infer some existence of the operators as some loop order in the low energy effective theory by using the information as we just discussed about. So I finally reached my conclusion. So in this talk, I recently that people have uncovered a very, I call it very minimal structure of the selection rules. And in fact, that we have all encountered with it in our daily life from the first day of the particle physics when we learned group theory. However, that we not pay attention to, we're not paying attention to them. And these are the selection rules that we call non-invertible selection rules. And so they may appear quite exotic from a conventional perspective. And in fact, that they are not that exotic in my opinion. And this structure is kind of minimal. So since they are minimal, so they are less rigid on the radiative corrections. And we try to understand them from the perspective of Spurion analysis in this talk. And here I listed just a couple of questions I thought which is interesting. So the first one maybe is that what are the other possible obstructions to the loop-induced violations of this class of selection rules? And as many people know that one obstruction is the most familiar one, that we can try to complete the particles into representations of some group. And then this will obstructing the violations. And secondly, we can do it by decoupling some particles in my algebra, right? This is also possible. And for instance, one can also impose something like supersymmetry, because that, there's a perturbative non-renormalization theorem for the superpotential in the supersymmetric theories. And also that one can do it using the locality in the extra dimensions, in the sense that I can put different elements at different positions in the extra dimension, and the locality should play some role. And so maybe the most interesting models, if you're a model builder, then maybe you can try to construct very interesting models by combining all these different elements. And secondly, the second question I'm interested in is that, are there any alternative UV completions of these selection rules apart from the string theory? Okay, so in case that we don't find any, then maybe this kind of a selection rule will be another low energy probe of the string theory. In case that we might confirm the existence of this structure from any experiment, then it will just point out in the deep UV on the string theory. So finally, that I would like to say that maybe we should perhaps even be more open-minded, and we might not even know all the possible selection rules that can govern the scatterings of the dynamical particles and also the dynamical particles with the defect. Okay, thank you so much.
Okay, we're quite a bit over time, so maybe someone has just one quick question.
Okay, so the way I understand what you're doing is you're sort of taking all the tree level diagrams and you're using sort of the fusion of the operators in your tree level diagrams to define some fusion algebra. And then your non-invertible symmetry or non-invertible selection rules are essentially saying what are the you're using this fusion algebra to say what are all the diagrams you could even write down that's consistent with your tree level diagrams.
Right.
So when you go from the UV to the IR, I think you're not actually picking up along some RG flow. Sorry, essentially when you do your Spurion analysis, you're saying sort of like you're using this extra diagram, or you're using this extra vertex at tree level that you're essentially adding into your Lagrangian and saying how does that modify my algebra. So, but when you go from when you do this deformation, you go from the UV to the IR, for example. I think you're not picking out a subalgebra because you're not actually, essentially you're deleting something that exists in your fusion algebra. So what is like mathematically this thing that you're doing? You're doing some sort of projection. Can you say more about what that is, and sort of if you could use that to describe more generally RG flows?
In general, you can construct two theories, one in the UV, one in the IR, using different algebras.
I give you a UV theory, and I ask you, what are all the possible RG flows? Maybe you would say there's some projection operator you can apply to your algebra.
Right.
So what is that operation? Because you don't necessarily need to project on a generator. You can project on like products.
Right.
Like what is?
Yeah, I don't know the mathematical answer to that. Yeah. Thank you.
Let's thank the speaker again.
Okay, thank you.